Chapter 3. Chapter 3 is going to look at rotational motion. Rotational motion versus translational motion. So let's just think a little bit about what would make something rotate. Now, everything in Chapter 2 was concurrent. The forces all came together at a single point, and if everything's tugging at just one point, nothing in this system is going to rotate. Okay, that made Chapter 2 a lot simpler. So this balloon will move up and down and sideways, but it's not going to rotate, and the reason it's not rotating is because everything is coming together at a single point. And our equilibrium was concerned not with something rotating, but just stopping it from moving. We don't want it to move in the X direction, not in the Y direction, not in the Z direction. So it's just straight line, up and down, translational motion. And we were able to only worry about this chunk of it because everything was connected at a point. Chapter 3, how this is changing is instead of everything coming together at a point, we now have forces acting at different positions on an object. So here's a force up here, and there's another force down here, and the distance between where these forces are applied, that distance is what actually creates the rotational motion. So whether it's a two-dimensional system or a three-dimensional system, when the forces are not all at a single point, when they're acting at different positions on an object, this is where it starts rotating as well as translating. So we have Fx, Fy, Fz. If those add to 0, it's not going to have translational motion. And the new piece of it for Chapter 3 is moments. We're going to be adding the moments together to 0 for no rotational motion. Moments are also a vector, just like forces are a vector. And the moments are going to describe rotating around the x-axis, rotating around the y-axis, around the z-axis, or some combination of it. The moment is a vector that describes the axis that it is rotating around. So force is a vector that describes the direction of the force. Moment is a vector that describes the axis it's trying to rotate around. What is a moment? Let's just better define this and think about what it really is. Okay, a force, some force that is applied to an object can create two different kinds of motion. And in statics, these are the two different motions we're trying to stop. The force can push an object in a straight line, so translational motion. The force can also rotate the object. And the rotation again happens when you have two different forces that are separated by some distance. That's when you're going to start to have rotational motion. So moments are what create and describe rotational motion. So because that rotation, it has to have both a distance and a force, that is how we're going to define the moment. So a moment is the force, the magnitude of the force, times the distance between the axis it's rotating around and where the force is. So the units on this are a little bit strange. The units are whatever the units for force is times the unit for distance. So this could be Newton meters, it could be pound inch, any kind of force times any kind of a distance. That's the unit for a moment. Moment also has a direction. It's a vector. In this case, if we put a coordinate system on here, so we have x to the right, y up, and then z coming out of the board. So for this example, our moment would be in the k direction because this would be rotating around the k axis. So it has units of a force times a distance. It has a direction. The direction is describing what axis it's rotating around. And that is what's going to help us define what rotational motion is. One more thing concerning the position vector and the force. So again, we have what it's rotating and the distance between that axis of rotation and where the force is applied. And these two quantities have to be perpendicular to one another. They have to be at 90 degrees to one another. And so we're also going to be reviewing what cross products are. This is one of the primary purposes that cross products are used, are defining moments for something. The name of the game for statics and a lot of engineering projects is stability. How do you keep things stable? If it is going to fail, how is it going to fail? And it turns out a lot of the different failures that happen because of rotational motion. Anything tipping over, any kind of balancing problems, this is all rotational motion we're talking about. So it's a very important part of designing for stability. Okay, talking through this cross product thing again. Let's say we have a force applied to this wrench, and we can break that force up into its x and y components, whether you take it over the top or around the bottom, and think about what each piece of this, what kind of motion each piece of that force is creating. Now the x force, this chunk of it is not going to rotate it. It's going to push and pull and create translational motion, but it's not going to rotate it. And if you think about it, it's only this y piece. The y part of the force is what makes it rotate. And this is that 90-degree angle again showing up, and this is where we're going to have to look at cross products, because what we're really interested in is finding which piece of the force is perpendicular to that position vector, linking where the axis of rotation is and where that force is applied. Let's review cross products, and hopefully you've seen this before in math and some other classes, but think through it again. Don't just memorize the pattern. Know where that pattern comes from. So I want to walk through where these cross product patterns come from. So what we have here is just a generic system. Let's say we have a piece of plywood and there's a nail on it somewhere, and you're going to apply a force on it. So for this example, we have a position vector. It's not just horizontal, it's not vertical, so we have kind of a random position vector with x and y components, and we have a force with x and y components. And the important parts here are the point that it's rotating around, the point that the force is applied to, and the direction of the force. The first step in all of these problems is to break everything up into their x and y components, and that applies to both your position vector and your force. So each of these pieces you're going to have to break into their x and y components. And once you've done that, we can walk through and see what combinations of these R's and F's are going to create rotational motion and which direction that rotational motion is in. Is it clockwise? Is it counterclockwise? Okay, so here's one combination. If we take the x component of the position vector and we combine that x component of the position vector with the y component of the force, of course x and y, those are at 90 degrees to one another, and this little combination, positive R, positive force, it's going to create a counterclockwise rotational motion. And that we're going to call positive. So, and you can think of it as a right hand rule. So if you wrap the fingers of your right hand around this nail, your thumb will stick out, or it's like unscrewing a screw. So if we unscrew a screw, it comes out of the board at us. So it's coming forward. We'll call that a positive combination. Here's another combination. So if we look at the y component of our position vector, and we're going to combine that with the x component of our force. And I know the x component is way over here. What we're really interested in is the line of action of the force. So it doesn't matter that the force is all the way to the right. It could have been all the way to the left. It's the distance from the axis to the line of action of the force. And you can see that this combination, our y with fx, is going to give us a clockwise rotation, which is negative. So this would be righty-tighty if you're screwing something into the board, so it's pushing it back, or the right-hand rule, if you wrap your fingers around it, your thumb is going to be sticking back into the board. So we get a negative rotation out of that y-x combination. Putting that together, this is the table that's usually used for those cross products. So for the k direction, and this rotation is happening around the axis coming out of the board. So we're looking at the z or the k direction. And we're going to get that from x times y. This was the positive combination minus r times x. This gave us the negative rotation. Another way we could have calculated this instead of using a cross product is just by using the angle between these vectors. And so if we look at the angle formed between the position vector and the force vector, we can split the force into which piece of it is in the same direction of r. So this f cosine theta, that's not going to rotate it. That's just tugging on the nail. The piece of the force that's going to rotate it is this perpendicular chunk. That's opposite of that angle, so that's the sine of it. So RF sine theta, this will get R, and then F sine theta is the chunk that's going to rotate it. That's the piece of the force that does all the work here. So these two are equivalent to one another. Whether you're going to use a cross product or you calculate the moment using the angle, these two methods will give you the exact same result. One more way to think about that angle. So rather than splitting the force into x and y components, we could have also split our position vector into perpendicular and parallel components. So same angle on each side here, and now we're splitting our position vector into which piece is perpendicular to the line of action of the force. The line of action of the force is really important. So here's the perpendicular combination, and of course that's the same thing that we saw before. So whether we say F r sine theta or R F sine theta, it's the same numerical result. It's just a different way to think through what it looks like. So all of these will give you the same answer, and it's important to see all of the different ways to get these perpendicular relationships, because depending on the geometry that's given you for a problem or how something is defined, one of these methods might be a little bit easier than the other to use in your homework. So once again, the two different ways of looking at this, we have the axis of rotation here, and walking up the lever arm, the force is applied here. And to find the perpendicular relationship, we can do a couple different things. We can either break this position vector up into which chunk is perpendicular to the force and which chunk isn't. So we have r sine theta. So this is the chunk, whether you use the angle up here, the angle down here, this is the chunk that's going to be perpendicular to your force. So that's one way to break it up. Another way to break it up is to figure out which piece of your force is perpendicular. So if we draw the position vector and then just draw a line perpendicular to that right through where the force is acting, we can split our force into which piece. This is kind of like a normal and tangent component of our force. So which piece is perpendicular and which is not, and it's the same exact equation, it's the same numbers, it's just a different way of looking at it. Here's the full cross product in all three directions. In the I direction, you're going to jump over yz minus zy. You're going to put that position vector in the front. Next, in the j direction, you're going to go opposite. Start in the right-hand corner and come down. Zx minus xz. And then in the k direction, xy, yx. So you can see all of, all of the coordinate systems are perpendicular to one another. So x, y, z goes with one another, and you can see it's always what's perpendicular to everything.